All right, so like I said, once you know Ka, you can calculate the equilibrium concentrations of the acid, the conjugate base, and the H3O, depending on what you're given. And so you can actually then solve for pH. You can find out what the pH of a particular acid will be. So again, we're going to be setting up an ice chart. And again, I just want to point out to you that X was negligible compared to the concentration of nicotinic acid. So when we found out that, or another way to think of it was the degree of dissociation was under 5%. So the fact that that was so small, we could ignore it when subtracting. And so that's going to be a key to making our life, like I said, easier, because we won't have to use the quadratic equation very much. So degree of ionization depends both on Ka and the concentration of the acid. And like I said, pretty much if it's less than 5%, we're going to be able to use this little trick. The way to tell if ionization is less than 5% is to look at this value, Ca over Ka. If you take the concentration of the acid, Ca stands for concentration of the acid, divide it by the Ka, and if it's greater than 100, that means that X is negligible. In our last example, the Ca was 0.012, and off the top of my head, I can't remember the Ka, but it was something like 4 times 10 to the minus fifth. So if you take that, that ends up being 255, which is definitely greater than 100. And we saw that in that case, the X was negligible. So it's kind of one or the other. Usually it's harder to do the dissociation percent, but you always have the Ca and the Ka, so you can find out if it's greater than 100, which means dissociation is less than 5%. And so what we're going to do is we're going to simplify when we do a problem. When we subtract the X in the denominator, we're going to make a simplifying assumption, and we're going to drop it and make it easy to solve. Now, if this is not valid, if Ca over Ka is less than 100, that means that this assumption is not valid and X is not going to be much smaller than Ca, and so you have to use the quadratic equation. Okay, so let's do another example. Calculate the pH of a 0.3 molar solution of acetic acid. If you didn't already know, the Ka value for acetic acid, it was given in that chart, 1.7, I think, times 10 to the minus fifth. Anyway, the first thing you want to do is write your acid equilibrium equation. So there's our acetic acid. Just write the dissociation plus water gives us H3O plus C2H3O2 negative. Write the Ka expression. Ka equals H3O plus times the acetate ion divided by acetic acid. You need to, in this case, we know what Ka is. Then we're going to set up our ice chart. Our initial concentration of acid is 0.3. Our H3O plus and acetate ions are 0. So we're going to lose a certain amount would dissociate. We're going to call that X, so that's minus X, and that means we'll get plus X of each of the others on the right-hand side. So at equilibrium, we have 0.3 minus X, X and X. We plug that into our equilibrium expression. So Ka equals 1.7 times 10 to the minus 5 equals X squared over 0.3 minus X. So like I said, if you wanted to solve this for X, it would be, you would have to use the quadratic equation. It would take some rearranging. It's not super hard. You all could do it, but we're all into trying to make things a little bit easier. So we're going to try to see if our assumption, if our simplification substitution will work. So in other words, if we could get rid of this minus X, if we could say Well, X is so much smaller than 0.3 that it's negligible when subtracting. Now, it's never going to be negligible when multiplying, obviously, but when subtracting, is X much, much smaller than 0.3 that to any significant figure rounding that it will be the same. So what do we do that? What we want is CA over KA. So CA, which is just from the problem, 0.3, divided by KA, which is 1.7 times 10 to the minus 5, is 17,000, about 17,000. So clearly that's much greater than 100. So what that tells us, and I don't want you to omit this. I want you to, when you're writing a problem, I want you to write this down, because if you're doing a mathematical proof, you don't just say, well, oh yeah, that equals X squared over 0.3. You want to say why you're doing that. So this is a way that you could say, well, since CA over KA is greater than 100, then that means, by what we defined, X is going to be much less than 0.30. So we can ignore it. So you want to put some of that into your problem when you're doing it. We can assume that X is negligible compared to 0.3. Okay, so since X is much less than 0.3, we're going to ignore it here. And so now we can just solve for X, multiply both sides by 0.3, take the square root, and we get 2.3 times 10 to the minus 3. And what is that equal to again? It's equal to X, which we also know is equal to H3O plus, which is also equal to the acetate ion. And we know that the HC2H3O2 is equal to 0.30 minus 2.3 times 10 to the minus 3, or 0.0023. So we can see that to 2 decimal places, this still rounds to 0.30. So our assumption was correct, so that's good. And now, because we know H plus, H3O plus, we can find the pH of the solution. And clearly, this is much less acidic than it would be if it was a strong acid, because it's not dissociating completely. If you were to solve the quadratic equation, I did solve the quadratic equation and I got exactly the same answer, 2.65. So you don't have to solve it. Obviously, we're getting all these things to make it easier, so we don't have to solve it. But just to show you that because it's less than 5% dissociation, the quadratic equation, this answer will give us the same answer. So we're close enough. Like I said, we already have good reason to assume that X is much smaller, but if I said what's the percent ionization, you can do that. 2.3 times 10 to the minus 3 divided by 0.3 times 100 it's less than 1% dissociation. So because the Ca over Ka is greater than 100, that means the ionization is less than 5%. So we're valid. But if you wanted to complete your proof and write that, you can do that and say it's definitely less than 5%. So our assumption that X is much less than 0.30 is a valid assumption. And like I said, the quadratic equation would have given us the correct answer, but it was not significantly different from the answer we did get, so that's fine. If we compare the pH of a solution to a strong acid of the same concentration, let's say we had 0.3 molar HCl, that would give us a pH of 0.52. So clearly, weaker acid means it's much less acidic. The pH is much higher for the strong acid. And that's because it completely dissociates. So the stronger the acid, the larger the Ka, and the lower the pH of that solution will be. All right, so I have one more example. This one is going to not give us the, oh wait, let's see. Well, let's try it. Let's just one more example. What I want you to note here is that we don't have a concentration, so we're going to have to figure out the concentration. So acetylsalicylic acid, which is aspirin, HC9H7O4. We dissolve 0.325 grams in 0.5 liters of water. There's the Ka. What is the pH? So we're just, it's the same basic problem. We just have to do a little more finagling here at the beginning. So we know the molar mass of aspirin is 180.2. So we can find 0.325 grams divided by 180.2 gives us 1.8 times 10 to the minus 3 moles. There's 1.8 times 10 to the minus 3 moles is put in a half a liter, 0.5. So we have to divide by the volume. So our concentration is 0.0036 molar. Since the Ka, you probably could use 3 significant figures here, but the Ka it only has 2, so we're just going to keep 2 in this case. All right, so now it's basically 0.0036 molar solution. What's the pH? Note that if we take Ca over Ka, we get 11. Clearly not greater than 100, which means that dissociation is greater than 5%, and so we can't say X is not necessarily less than 0.0036. It could be on the same order, or at least not to the significant figure. So we can't make that assumption. So we have to use the quadratic equation. So I guess I've worked through this so that you can see it. We can set up our ice chart. So X is our H plus, X is our acetylsalicylate ion, and then 0.0036 minus X. So there's our ice chart. Plug that into the equation. And we have Ka. Plug that in. X squared over 0.0036 minus X. We have to use the quadratic equation, so I guess I promise I won't put one on the test. Excuse me, but there may be some homework problems that need it. So let's work through this one. Let's get a good review of algebra. The first thing we want to do, let's see, is multiply both sides. Multiply both sides by that. So we have X squared. Then we're going to have to distribute. So let's see what I did. Yeah, remember that you always want the quadratic equation, you always want it in terms of ax squared plus bx plus c equals 0. So we have to arrange it to get it like that. So the first thing we do is we multiply both sides by 0.0036 minus x. But what we're going to have to do is we're going to have to distribute. So 3.3 times 10 to the minus 4th times 0.0036 is 1.2 times 10 to the minus 6, and then 3.3 times 10 to the minus 4 minus x is equal to negative 3.3 times 10 to the minus 4x. So now we need to get everything on the same side, so we're going to add, we have to add 3.3 times 10 to the minus 4x to both sides. And then we want 0 on this side, so we're going to have to subtract. So now we have our quadratic, or we've got it in that form. So A equals 1, B equals 3.3 times 10 to the minus 4, and C, don't forget the negative, C equals negative 1.2 times 10 to the minus 6. You can put that in the quadratic equation, opposite of B plus or minus square root of B squared minus 4AC all over 2A. There we go. Let's erase this so you can see that. And then, right, so A equals 1, B equals 3.3 times 10 to the minus 4, and C equals negative 1.2 times 10 to the minus 6. A lot of times what I'll do is just find a quadratic equation solver online. And I did it looks like I plugged it all in, but you can find a quadratic equation solver online as well. Here are our two answers. Because it's quadratic, it should have two answers. One of them is not going to work. Remember, our concentration was 0.0036 molar. So since we can't really have a negative concentration, that one's going to have to be the one that we omit. So X is going to be equal to 9.4 times 10 to the minus 4. Remember that that equals H3O plus, also equals the aspirin C9H7O4, the conjugate acid. And since that equals H plus, then we can find the pH. So pH equals 3.03. If I didn't use the quadratic equation, the answer would be 2.96. Now you might say, isn't that close enough? Well, depends on what you're doing. Since you didn't get exactly the same answer, and by using our rules, we needed to use the quadratic equation. In the last example, when we didn't need to use the quadratic equation and we did use it, it gave us exactly the same answer to the same two decimal places. So yeah, it's a little bit off. So we did need to use the quadratic. All right, polyprotic acids. Some acids have more than one protons, as we've seen, and they can donate them in turn. So these are called polyprotic because they have more than one proton. Sulfuric acid is an example of that. H2SO4 can give up one to become HSO4 negative, and then it can lose the second one to become SO4 negative too. And as I talked about earlier, they each have their own Ka value. So actually, H2SO4 being one of those strong acids has a very large Ka for the first one that we don't really ever use, but there is a Ka for the second one. Another example is carbonic acid. In this case, both of them are considered weak acids. So here we have our first equilibrium where one H is removed, and then we have our second equilibrium where another H is removed. And remember, we looked earlier, the Ka for the first one should be a larger number than the Ka for the second one because it's harder to remove an H plus from something that's already negative because they're attracted to each other. So harder to remove that second one, but you can. What happens now, generally, as we see, I'm going to do an example here in a second, and as you'll see, actually, the pH will really come about from the first ionization. The second ionization is not that important in terms of the pH. It's negligible. But what if you wanted to know the concentration of the conjugate of the second equilibrium? You're going to have to go through a couple of examples. So a couple of calculation. So that's what I'm going to do in a second. But each one has a Ka value, like I said. So the Ka for the first one is, and if you look on the chart, it's 4.3 times 10 to the minus 7th. So that's to lose the first H plus. And then the second one to lose the second H plus. And notice, like I said, it's a much smaller number, 4.8 times 10 to the minus 11. So that's why the pH is not really affected by the second equilibrium, but yeah, like I said, the second one will be will be smaller. If there's a triprotic acid like H3PO4, there'll be 3 ionization constants. It might appear complicated to calculate our equilibrium, and we're going to make some assumptions and we're going to work through it. And so we'll see. We'll see that in this example. All right, so ascorbic acid is a diprotic acid, H2. So both of those hydrogens are acidic, so we can have 2 equilibrium expressions, two problems to solve. So the question is, what is the pH of a 0.1 molar solution? And the other question is, what is the concentration of the ascorbate ion, meaning after it's lost 2 hydrogen? And as we'll see, like I said, the pH will really only be affected by the first equilibrium, but we're going to do the second equilibrium as well, so that you can I can prove that to you. And but we'll have to be able to find the ascorbate ion, we're going to have to do the second equilibrium. So we have, and it's not as bad as it sounds. And like I said, there might be one on the homework. Probably won't give you one on the test, but I would kind of figure out, I would pay attention to what I'm doing. All right, so like I said, when looking at pH, the Ka2 is so much smaller that we can neglect the second reaction, but we have to do it to find the ascorbate. So let's go for it. Okay, so here's the first, down here at the bottom is the first ionization. The ascorbic acid loses its first proton to give us HASC. So let's go ahead and just worry about the first equilibrium here and set it. So if the initial concentration is 0.1 molar, you can see the H3O plus 0, 0, plus X, and so we have our equilibrium concentrations, and we can say we've got our Ka1, and so we can solve, and also note that Ca over Ka is greater than. So there's our equilibrium expression to solve for X. Since Ca over Ka is greater than 100, we can solve for X, and it's 0.0028. So remember, what is that? That's equal to the H3O plus, and it's also equal to the H ascorbic, the concentration of after it's lost 1 H. Okay, we can figure out the pH if we wanted to at this point, just to see what the difference are. Let's see. Yep, so pH is 2.55 if you take the negative log of 0.0028. All right, so that answers that question, and actually what we'll do is compare it after we do the second equilibrium and just prove to ourselves that the change in pH is negligible after the second equilibrium. But we're going to use the second equilibrium because that's the only way that we can find the ascorbate ion concentration. So what we're going to do is we're going to set up another equilibrium, the second equilibrium, a second ice chart. And so here's a H ascorbate plus H2O gives us our ascorbate ion. This would be hydrogen ascorbate, I guess, and then the pure ascorbate. So this is our second equilibrium. Now we can set up an ice chart for the second one. We know the Ka for that one is 1.6 times 10 to the minus 12. So let's do that. Our initial concentration of H ascorbate, hydrogen ascorbate, is 0.0028. We figured that out after the first equilibrium. So it's no longer 0.1 because only a small percentage has dissociated to the HASC. So that's 0.0028. And just to distinguish, we're going to call the amount that dissociates from that Y, just because we're going to keep it separate from X. Now, it's not only the H ascorbate that is 0.0028, but we also figured out that because of the first equilibrium, we also have some H3O plus even before the second equilibrium takes place, and that's 0.0028, but we don't have any ascorbate. So we have plus Y, minus Y, and then 0.0028 plus Y, and 0.0028 minus Y. So we can plug that into our second equation. Plug that in. And we can also see that Ca, obviously, if the first one was negligible, the second one's going to be negligible. So Ca over Ka, 0.0028 divided by 1.6 times 10 to the minus 12 is clearly going to be greater than 100. So not only can we drop the plus y, the minus y, we can drop the plus y as well. So this one's easy to solve because y just equals 1.6 times 10 to the minus 12th. So that means the ascorbate ion is 1.6 times 10 to the minus 12th molar. And also we know that that's, so what is our H plus concentration? Our H plus concentration is 0.0028 plus 1.6 times 10 to the minus 12, which clearly is much, much smaller than 0.0028. And so the H plus from the second ionization is very, very small compared to the first ionization. So if you're just looking for the pH and there's two ionizations, you only need to worry about the first ionization to get a good idea of what the pH is. So we can ignore the second equilibrium.